good to be able to interact and what relevance may have what I have been doing of late. Now, first, and I have already here, but I think the most important is to make a setting in this context. We are talking about many body systems which tend to boil down to a line of atoms interacting. But of course, there's much more than that. And there's the question of whether the system may have or not a classical correspondence. Everything that I say here has to do with systems with classical correspondence. So if you want, you can imagine that we have a hot protein molecule with lots of atoms. Of course, the atoms all have their positions, so we don't have any, they're all distinguishable because they're all placed there inside of the molecule, but they vibrate in a way which is not, of course, harmonic oscillator. Now, then you have a huge energy shell, which is classical in a huge space. Doesn't matter how many degrees of freedom you have. It's finite, but there it is. So there's this energy shell. And let's just remember that whatever the number of degrees of freedom, there will be, if it is not integrable, it will be generally densely populated with periodic orbits, of which there's one which has a minimum time. And we can look at this movement for increasing time. Now, as we increase the time, we can think that we look at a scale of energies which decreases correspondingly. And the longer the time, the smaller the energy scale. But so you have energy scales because this is a huge system, which no matter how little the energy scale will have a lot of states. And in fact, if this is a big system, you might have difficulty if you're thinking in real terms that you can pinpoint an actual energy level. So let's think about slightly fattened microcanonical ensemble and classical energy shells. Now, if the time scale is short enough, you'll have the density of states will be vial, just the volume inside the shell. And when you increase the time and decrease the energy, you come to the first periodic orbit, and then the density of states will start to show oscillations and things which are truly quantum start to come in. Now, what I emphasize again is that this is a universal picture, and it will happen for all systems, no matter how big they are. You will have this state. Now, the second point before I start is that, of course, let's say our friend, the protein molecule, is a beautiful thing, but the reason you're interested in it is because of what it does. So most of the talk on chaotic system has been about how, looking at them, what's their spectrum, what's it like? And, but somehow, you have to start talking about how these systems act. So you have this hot molecule, and it will interact with things, and you want to do movement. Now, when you start to think of that, you start to think about what I call compound orbits. You're not just going to look at what the periodic orbits or open orbits are in a single system, but you're going to look at it, how it, let's say, you evolve the system, how it looks later. You look at correlations. For all that, already in 2016 with Olivier Brodier, we wrote a paper about correlations, how they evolve, and you come into these compound orbits. So what I'm going to now talk is, and let's say perhaps the simplest example of the use of compound orbits, and which then I hope that besides what I talk here, which is more or less concluded work, what more one can do, which might be interesting to the community we have here. Now, okay, so this doesn't work anymore, but I can do it here. Okay. This works. Oh, it's frozen now. Maybe I gave too long an introduction. It didn't like it.
What do you how do you unfreeze it once it freezes?
Okay. 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 Well, that's so the fact is that one doesn't usually start with very excited states, but let's go on with them anyway. So what I want to talk are transitions driven by general unitary operators. Now, as I said, for the system itself, we have the which way am I going? Yeah, good. Okay. Now, so you have the spectral Wigner function, which is an assembly of, so this is the representation of the density operator in this huge space that we have, 2n-dimensional. X is a point in the phase space. It's got position and momentum. And it's this Wigner function then represents in phase space the spectral density operator. And you have the window, which I said, which will depend on the time later. But here it is just it's got a width then over here. Now, we act on it with a unitary operator, which you can think as being an evolution. But the point is that in any case, this will be presumed to be a very quick operation that one does. This time this time will be small in comparison with the times of the system that we are looking at. And so it evolves a pure state into a unitarily. And we look then at the evolution of this spectral Wigner function. So you have an evolved driven spectral Wigner function. Now, the probability that the new system, after it has evolved, that for a transition from an energy shell E in the old system and E prime in the evolved system is just a trace of the two density operators, which is in the Weyl representation here, just the integral of the two spectral Wigner functions. Now, let's look at the smooth classical background of this. The first approximation to this Wigner function is just a delta function on the energy shell. Then the transition probability is just the integral over the overlap of these two Wigner functions, and which is just a classical probability. So you've got a probability density on one energy shell, another energy shell which has evolved, they intersect, and the product of the two probabilities gives you the probability of transition. That's the intersection. So here you have the one energy shell of energy E. The driven system is now this one over here, and they intersect, and the intersection here is what you do, and the integral it can be shown to be just the Poisson bracket of the two classical Hamiltonians, the original Hamiltonian and the evolved Hamiltonian, one over that, and the Poisson bracket, of course, being just this over here. Now, you obviously then, as you take these two energy shells and they touch, they may be tangent, and this will be a caustic of the transition, which of course becomes more pronounced classically, but in quantum mechanics you will soften this with Airy functions, which approximate the delta function and which have a peak and they are oscillatory on one side and evanescent on the other side. Okay. Now, the point is that this is the classical picture. Now, in the same way that for the static energy shell, you have the shell, and when you start to look at longer times, you get narrower shells, and you get then start to get periodic orbits on top of your classical picture. Here, you will have these compound orbits. And the point is that you see how do you get these compound orbits, which I will talk. You have the two energy shells and they intersect. Now, when there are hypersurfaces in the phase space, and usually you think of, you have an energy shell and you cut it with a plane and you get a Poincare section of that with the hypersurface, which is a plane. But you can use the other shell as a Poincare section in the same way of the energy shell. And instead of just looking at the orbits of one shell, you can look at the orbits of one shell and then match it onto orbits which come back on the other shell, right? And when these orbits, now you then have a Poincare map going, a Poincare map returning. So you have the product of two Poincare maps, and the fixed point of the product of the two Poincare maps gives you a compound closed orbit, which goes one way and comes back the other way. And these are objects which we will be working. Now the point is that, so here they are. Now you look at the same figure. Instead of thinking of this as being the energy shell itself, you can think of this as a single trajectory, which was in this energy shell, matching up to a single trajectory which comes back. And these exist because they are fixed points of a well-defined Poincare map, right? Now, as you change energies, this family, you get a family of compound trajectories, a smooth family, and which is parameterized by energy, but each one has its own time. So you can switch from energy to time and consider then that you have families of compound trajectories in phase space parameterized by time instead of energy. So let's look at them. Then these compounds, let's go then into time and consider compound evolution operators, which is what the work with Brodier actually was working with. So but now I'm not talking of the evolution of the state of the whole system. I'm talking about internal time. I'm talking about this time which I said when you talk of a single system and you can consider energy and time as being, and so you have trajectories in the system. So this is before each system, the initial system and the driven system have its own internal time and its own trajectories. And being that the unitary evolution from one to the other corresponds to a canonical classical evolution between them, which takes the trajectories of one into the trajectories of the other. Now, so you have these two evolution operators, and you can look then at the compound evolution in time of one and the other. And these trajectories that we have obtained in energy, you get in time. You have one system, and then you evolve with the other system. Now, just as with a normal periodic orbit, the trace of a compound operator has this familiar appearance, which appears in the Gutzwiller trace formula. But here I'm still talking with time. Actually, with the Gutzwiller trace formula, everything, all these trajectories appear also, the trace of the trajectories in time appear. And of course, it's much simpler because whereas in an energy shell, you have loads of trajectories, you fix the time, for a simple system, you will have a single orbit. Now, you have these here, and the action of these trace is the action which I showed before in energy with 2 times appearing here, because that's what we have put in. And the derivative of this generating function or action gives you the energy and the time bucket. Now remember here there is an the amplitude is given by the monodromy matrix over here, and this is just the product of the two. You have evolved in one way, you have come back in the other. Okay. Then what you do, since I have little time, is that you take what we were looking for, just as you get the spectral Wigner function as the Fourier transform of the propagator. Here you get the transition density as the double Fourier transform of this, coming here, of the the trace of this thing which we had before. So here we have finally the energy transition density as the double Fourier transform of this trace of the compound propagator. And so here you have the oscillatory terms, which you have to add to the classical transition that we have before. And the long compound trajectories will be dampened with this energy width, which I have put the same for both energies here. And the difference is that, okay, so you have something which comes out. And so let's end with the discussion. First, I have hidden all the Weyl-Wigner scaffolding, which I used to calculate this, so it's not encumbered, but of course, this is what the instrument which you really, you can try to do it in other ways, but you don't see what you're doing if you're not working in phase space. I get the phase and the amplitude of the contributions in any case in a way which is independent of the representation which I used to do it. In the first time I did it, it did not come out for the amplitude, but now it does. The first paper which I cited before in the beginning, the action, the transformation was just a reflection in phase space because of the way that I started with the Weyl representation depends on these reflection operators. In any case, even though that's a sudden operator, I gave straight away the unitary transformation. I have written here in terms of a Hamiltonian, but you must think of this as being a fast process so that nothing has come in. Of course, if you try to go to small windows, you will have convergence problems, and this is would have to be dealt with, but I don't know whether one really needs it. And so here to finish off a comparison of what one has done here. On the right, you have look at the trace of the evolution operator, take its Fourier transform, you get the smooth density of states. The semi-classical evaluation explains this in terms of periodic orbits in an energy shell with repetition, and you get the Wigner-Wutzwiller trace formula. Here, I have started from the compound evolution operator. I take the Fourier transform in double time, and I get this smooth density of energy transitions. Then the semi-classical evolution is obtained in terms of closed compound orbits joining the E shell with the driven E prime shell, and no repetitions. Note that if you've got, one thing is the periodic orbit, but if you're going and you come back, then the repetitions don't come into this. Right? And so you've got a kind of compound trace formula to give you the energy transition. So that's I think the example of the kind of thing one can do semi-classically when you start to play around with compound orbits. Thank you. Yes, if you're working in time, which is what one was doing with Olivier, which is to look at which comes into looking at evolving correlations in phase space. The idea being that if you've got an observable and you relate it to the Wigner distribution, you're representing it in terms of reflection operators, which are also unitary, so that everything becomes, each operator, even the observables, goes into a kind of large compound polygon. And you take the trace of that to get the correlation. Now, the point is that you can do initial values and get away from searching. You start at one point and you come back to the other. Yes, there are initial value representations for getting at the orbit. Well, what one can do more is to look at. I think it's more useful to do what Marcos Aguiar did, which is to, once you've got the orbits, to follow them in energy using Newton methods, using the continuously. Then they bifurcate and go everywhere, and you follow the bifurcations and this kind of thing. Right. Yes, I think that could be what. Yes, the thing is that here one is of course for each shell you've got those orbits that come in. Now the point here that of course you're going to look at pairs of energy which go everywhere, and you have each one of them to do against. But maybe it's possible. How does it fit? Okay. Okay. So let's see.
So good afternoon. So first, let me thank the organizers for the invitation. So the organizer asked me to not to give really a talk, more like just giving some list of things that I'm interested. So that is the title of the talk. That of course makes no sense. One holds PT symmetry, SYK model, periodic orbit. So I will try just to make some sense of it during this talk. So, but before that, let me thank some of my collaborators that in the last few years have been working on these problems. So what I want to say in this talk is basically relate these concepts. One is the what is called such objective time model. So I will tell you that I don't like this name, but what it is. And so these are models of Majorana's fermions with infinite range interaction and in 0 dimensions. So this is IJKL. They are index impact space. So I want to relate that to many body quantum chaos and to quantum gravity. And so that would be the first part of my talk. That is for Hermitian systems. Then I will extend the relation between these three concepts to non-Hermitian systems, to dissipative quantum chaos. I don't think I will have time, but if not, if I have time, I will relate quantum gravity to periodic orbit theory. So let's start. So let's start with quantum chaos. So this is what we all know. Quantum chaos is the quantum mechanics of classically chaotic systems. So why quantum chaos is interesting? So why we study quantum chaos? Because it's universal. So it's like the starting of the novel of Tolstoy, Juana Karenina. All families are alike. Each unhappy family is unhappy in its own way. So what that means is that all systems that are chaotic are similarly chaotic. This is why we study, because for a long time they behave the same. So they only depend on the symmetries of the system. They do not depend on the details of the dynamics. However, systems which are integrable, of course, are very interesting, but you have to study one by one. So in quantum chaos, you can avoid that. You just identify universal properties. Another question is, which are these universal properties? So these universal properties, one is one due to Ozorio, but of course, somebody we should mention here especially. And the Boicas-Giannoni-Smith conjecture just tell us that this universality is reflected when you study level statistics at the level of the mid-level spacing. So the Heisenberg time. So for a long time, the correlations in the spectrum, they do not depend on the system. They are well described for any quantum chaotic system by random metrics as random metrics theory, assuming that you don't have undersold localization or another specific quantum phenomenon that happens in sometimes. So this also was Polyafetov did prove that analytically for the case of disorder systems in higher dimensions. Now the issue is that this is not the only way that universality enters in quantum chaos. The other way is through, if we compute the square of correlators. I like more like calling that way that out of time correlation functions, because that reflects that this type of operator, the square of operators, if you go to a textbook in quantum mechanics, are related to the growth of uncertainty, quantum uncertainty. So you have a wave packet, you prepare in a quasi-classical state, you let evolve, and this type of commutators tell you when quantum correction become important. And now the important result that it was first by Larkin, then in the 60s, in the 70s, well, there were many papers with Keith Rotors and Salavsky, Berman, besides few. So what they found is that quantum chaos is characterized by exponential growth of this out of time correlation function. So that reflects when this become of the order one, defined at time scale, that is called NFS time. Now many people call it scrambling time. So that is the typical time that quantum effects become important. And it's universal in the sense that is for all chaotic systems is exponential. Is controlled by this lambda is non-universal, which is the classical Lyapunov exponent. It would be more accurate to say the leading Lyapunov exponent, because a classical system could have many Lyapunov exponents. However, for systems which are not chaotic, typically we will have is power law instead of exponential. So these are the two things that or two characteristics of quantum chaos. Now, why is this related to quantum gravity? So this story started more like 50 years ago with these guys, the little bit hand waving guys. These guys, Preskill, especially Saskin, what they said basically is that, so you have a horizon, close to a horizon in gravity, you just throw a particle, a charged particle fixed, and then you wait till this particle cover the horizon or get very, very close to the horizon. This is called a stretch horizon. And then you count the time. How long does it take? Close to a horizon in gravity, you have something which is linear geometry that is universal. For almost all systems with horizon in gravity, they have this property, and they identify some logarithmic time in terms of power law, which power law is what you get if you do any type of calculation. And they famously said that quantum black holes are faster scrambled in nature, because this type of scale logarithmic instead of power law is related, they relate that to some sort of quantum time. But this is completely hand waving. Of course, maybe other experts in gravity can explain that better. But for many years, people were talking about this type of scrambling time in gravity that with no very sound argument. This changed completely in 2015, that it was not proved, it's conjecture, but it's conjecture based on like hard principles like analyticity and causality, that when you compute these, let's say these commutators, forget about this, why these are not important here. What they claim is that there is a universal bound for quantum chaotic system. So we said that this is exponential, but what they went was even before, even more than that. They said that the Lyapunov exponent in system, at least thermal systems, that is valid for a single particle, many body for every system. They only have to make some mild assumption about separation of scales. Is bound by this universal constant. And what is more important, what they said is that when this bound is saturated, so that means that lambda is equal to that, that corresponds to systems that have a holographic dual. So these are strongly correlated field theories that can be related to black holes, I mean to gravity backgrounds. That happened when this is equal. And then the problem is that even though they have this, they don't have one example to prove that, because actually this calculation typically is very complicated. As you know, compute Lyapunov exponent is complicated, either numerically or analytically. It's not possible in many cases. So then is when Kitaev enters in this game. So he knew this result, and then he found one system that this was saturated, a field theory system. This field theory system in zero dimension is nothing but what is called now the SYK model. So these are these fermions, 4 Majoranas. These are random couplings, and we see the saturation if we go to the low temperature or strong coupling limit. And this is what is called Sartre-Kitaev model. Especially in this audience, I want to emphasize, even though my talk is very short, I want to say that this infinite range model, they were known long before all this happened. They were known actually from the 70s by French and Boigas and Flores. Basically, these guys, they were nuclear physicists, so they want to do a model of the nuclei that was better than just a random matrix, like the Wigner idea. But still, they have some predictive power. So they were very popular for many years. Even there are books about this infinite range model. So then this paper by Sartre was one of these papers on this topic. But before, there was a huge literature that now the people in high energy do not cite. Though it's true that the first person that really relate infinite range models with maybe holographic dual was Sartre. Okay, let's forget about names. So why is SYK interesting? So this way SYK is interesting for the following reason. So in red is why it's interesting for people working on high energy physics, and in green is for people that are not working in that. So it's interesting because it has the symmetry of gravity. So remember your course about general relativity. So you have gravity is described by the Fermat-Fisen invariant. So this is the same that the conformal group, that in SY is the symmetry of the SYK. So for low temperatures, it's broken to SL2 symmetry. That is a symmetry that keeps some of the symmetries that you expect in gravity. And actually, it's the symmetry that you see in gravitational systems, quantum gravitational systems. And the duality, when we say that SYK is related to some gravity model, is because we can prove that both actions are the same. So it's a very strong statement. It's not some conjecture. So in this case, you can prove that the SYK for low temperature is described by what is called as Schwarzschild. So this F is the generator of these SL2 transformations. So people like this because you have a lot of analytic control. Now, other thing that people are interested in high energy is that the spectral density of this SYK model is not the semi-simple law, like for random matrices. So what you get is exponential growth of excitations, low energy excitations from the ground state. And this is typical of systems with, the exponential growth of excitation is typical of systems with conformal systems, and also black holes. It's a typical feature of black holes. And also it's because saturated bound. So that means that the saturation means that really by looking at this simple model field theory, you can make prediction about gravity. For other people, it's interesting because it's analytically practical. So that means you can do analytic calculation. It's very, very, very unusual that you can do this type of calculation analytical in a quantum chaotic system. And also because it's like a perfect example of random of quantum chaotic system, because agreement with random metrics is truly excellent. And also you can reproduce all the symmetries of random, all the possible ways that a system can be ergodic can be reproduced with the SYK model. So I just want to just mention one example of that. This was from my first paper on this topic. So we just compute level space distribution, and even the tail, even close to ground state, which is related to gravity or high energy excitations, they are really, really close to random metrics. Of course, we could discuss correction to random metrics, but that would be for a longer talk. And also what is important is by changing parameters in the model, like the number of Majoranas interacting, or just the number of Majoranas, you can reproduce different universality classes from the tenfold way. So these are different, these are chiral ensembles. So it's a model that is really a toy model of quantum chaos. So it has dynamics. So it's like one extension of random metrics because it has some dynamics, but it still keep you can describe any universality class. So now what I said was only SYK and let's say black holes, but also SYK has been used to describe other types of gravity configuration. So let's start with these traversable wormholes. And so this was, well, first, maybe I use the word wormholes, and you see the movies and science fiction. And actually this was also true in the gravity community to some extent, because these wormhole solutions that connect distant point in space-time, they were considered not physical. Or at least some people consider they were not physical, but this changed after this paper that basically they said that if you put a contact between these two by hand, that the 2 points distant point in space-time are connected, this wormhole solution did not break any universal law in physics. And they were considered like a solution of the equation of motion that should be taken into account. So based on this, Baldacena and Chi just studied this model. This is one SYK left, one SYK right, like two quantum dots, and they are connected by minimal interaction. This I that you see here is just to make this, the whole thing Hermitian, so it's not something non-Hermitian. And what they found is that they could find by studying the low energy effective action of this, it was some Schwarzschild, they could relate that to a model of a traversable wormhole in some gravity background. However, in this talk, I don't want to talk about wormholes. What I want to say is that what they found is also, they found something which from my point of view is very interesting from the point of view of field theory, which is the following, is that they found that when you put the two together in quantum mechanics, so if I put this together with some coupling lambda, of course, I'm going to have a ground state which is going to have a gap, because that you're putting by hand some tunneling, which lower the energy of the system. Okay, but what they found surprisingly is that even perturbatively, just pair something which is linear in lambda, you get some fractional power in lambda. And physically, that means that when lambda is very small, the gap is enhanced with respect to the perturbative limits. And these have very sound interpretation. Basically tell you that the strong interactions in each of these SYK, when you put them together, induce some enhancement of tunneling. Okay. Then if you hit the system, that disappears. Then you go a transition from this to some trivial gap. And so this, from my point of view, even if you forget about any wormhole, anything, is some new phenomenon, some physical new phenomenon in which interaction enhance tunnel. And also, we study, my first paper on this, we study the spectral statistics of this model. And then we found a transition from random matrix, from, let's say, the black hole phase, that is like the, yeah. You mean quadratic term, but you mean quadratic term, you mean if I change the coupling? Okay, this is a good question. Actually, let's say that when you see the 2/3, this 2/3 has to do with two things. Has to do with the number of here I'm considering 4 Majorana operators. Yeah, and one of these, I mean 1, 1. If I change these 2, I will get another power. So I won't get 2/3. For 2, I think you get like 3/5, I think. So that depends. So this exponent depends on the number of operators that I put here and the number of operators I put here. I can put 4, I can put 6, I can put 8. Okay, but that's not depend on the coupling. Only depend on these two things. That's not depend on the coupling. I mean on the J's. Assuming that this is a 0 temperature result. You go to high temperature. Then the coupling effectively is small, and then you don't see this phase. Okay, so that is just what I want to say about Hermitian. But now you can extend all these ideas to non-Hermitian systems. So that means that is to use SYK as a toy model for dissipative quantum chaos as an example. And this also has an interpretation in gravity. So this is what I'm going to explain here. So this is something we started like two years ago. So first, I'm going to say that SYK model is also very good at giving universality classes when you have a system which is not Hermitian. So in the same way that there are 10 different ergodic states for Hermitian systems, for non-Hermitian, there are 38 after this Japanese group that this paper of 2019. So in this paper, so we found that if you take a SYK model that with Q body, we use Q and 6 for our research, but these are couplings, these are complex couplings, so these are real Gaussian numbers, but they are complex. Then we can reproduce up to 90 universality classes, just with a simple model, just changing like the number of Majoranas here, or I mean the number of the Q body interaction, Q4, Q6, and the number of Majoranas here from 0 to M. So we could reproduce up to 19 symmetry classes by just changing things like, I mean, defining anti-unitary operators, chiral operators, particle operators, time reversal symmetry. So there is a whole classification of that. So I just want to emphasize that it's very good. It's a model which is very good if you want to study some specific system with a specific symmetries. And then using universality in quantum chaos could give you features that you can then check in systems that they are a little more realistic or they are not in 0 dimensions. So you can see the agreement with random metrics is very good. So these points, this line are the analytic prediction, and these are the numerical results. Also, we study long range spectral correlation. These are short range. So there are papers by people in the audience that they were looking at this, because actually the very field of dissipative quantum chaos, still we don't have a very sharp definition of what quantum chaos is, but now it's a problem that many people are interested. So I don't want to say more. I prefer then to move how these non-Hermitian SYK models are related also to gravity configurations. And so now, instead of doing what Malacena and she did, so you can take one left, one right, you don't put any coupling, And then you make this coupling complex. For the left, a complex number, and from the right, the complex conjugate. So this Hamiltonian has PT symmetric, which is very important. As you know, if you have followed Carl Bender, and many papers on that, and now has become a very popular system with PT symmetric, even though they are not Hermitian, they share many properties of Hermitian. So basically what we found is that even though left and right are not coupled, when you do ensemble average, they become effectively coupled. By effectively coupled, I mean that if you compute the free energy of this type of systems, you have a phase which is completely flat. That has to do with the fact that you have a ground state that it has a gap. But this gap is inconsistent if the two left and right, they are uncoupled. It's disorder, couple them. And then what you have is like some replica symmetry breaking. So you have like two copies of the system. So even though they are not uncoupled, for low temperatures, there is a phase in which they are effectively coupled and induce a first order phase transition in the system. So this is what we did that last year. Then before that, we have a show that actually this type of configuration SYK are equivalent to now Euclidean wormholes. So Euclidean wormholes are like, again, like in gravity, two things that are separated by some horizon, but then you can connect it. They are not related to tunneling, or because these are in Euclidean time. So you can make some solution in gravity. That we found that we could make a match between SYK and these gravity configurations. So now the next topic is, I said that one of the main issues in SYK now is to study non-Hermitian stuff. So before I said that some SYK with real and complex couplings, but there is a more physical way to see that. Is what if I put a SYK coupled to a thermal bath? Sorry, a Markovian bath. So then I can study what is the time evolution, the real time evolution, and then study what is really this dissipative effect induced by a Markovian bath. So we did that, and using the usual Lindblad formalism, and then what we found was that remember, when you do Keldysh, you need to divide the system when you do path integral in forward and backward in time. So effectively, you have to double the degree of freedom. So effectively, when you study time evolution of one SYK, you get two. No, it's not a specific of SYK, it's on any system that you do this Keldysh formalism. And then you see here that the Lindblad, the Euclidean that describes the system is very similar to the one that we saw before. Then we could do large N, then we can compute retarded Green functions. So then in this type of systems, when you compute retarded Green function for long times, the decay, the exponential decay, just tells you the equilibration time. So it's like I perturb the system relaxes to equilibrium, and then that depends on what is the coupling to the path. So let's forget, for a longer talk, I could explain this oscillation. So let's focus on that. So this is not analytic. So we just do numerics, but we found that this analytic, simple analytical expression fit the result very well. And then what we found was that how the equilibration time or the decay rate depend on the coupling to the environment. And then we found something surprising. We first thought that was wrong, is that even if there is no coupling between left and right, still, no coupling of this SYK with any bath, still we found that there was some decay to equilibrium. So some finite decay. And that is surprising because when you see the equations, left and right, in this Keldysh formalism, they are different. I mean, it's not coupled before you start the calculation. So actually, this is non-zero, even for mu equal to 0, because the system is Stroll interactive. So it's some sort of thermalization. So the system can thermalize even if you don't put in contact with anything. Now, if you put in contact a little bit, then actually nothing special happens. Just change a little bit with a weak couple to the environment. And then we see some non-monotonic behavior that in a longer talk, I would expand on this, but now I think just want to say that that has to do with quantum chaos, because if we study SYK with one body interaction, we don't see that. So that means that this is equal to 0. So you need some coupling to the environment to see some thermalization time. So how much time do you have? -5 minutes. Okay, then I will conclude. I will conclude here. I just want to say that this is also that it's possible to relate this configuration to gravity configuration, but now in the zeta space is something we are working. And okay, so then I stop here. So thank you very much. Which one? I don't know. No, maybe, but I don't think I. Yeah, okay. Then maybe was the first. Yeah, in one I mentioned information paradox, but I don't. No, has to be later. Wormholes. AES background, but not effective, play intelligence, something. Hawking page. Hawking page. No, it's just that when you study, that is just I mean, a name that I mean, when you study the systems, you have a first order phase transitions. Actually, I have it here. So this Hawking phase transition is a transition between this first order phase transition, and in this case, occur between a background that is controlled, or in the path integral is controlled by this one-hole solution, and then after this transition is the solution with two black holes become dominant. So basically, you don't have to think in terms of gravity. Is in terms of SYK, what happens is that you have a phase in which you have this enhanced channeling because of strong interaction. When you hit the system, in some point, this non-trivial phase disappears. And then what you have is simply a coupling between two systems, but it's not a complete chain of the ground state. You have like two SYKs, of course, they are coupled, but in a trivial way. And the other is when you have this non-trivial enhancement of the, for instance, of the gap, but there are other features that we will discuss. Yeah. Yeah. It's a matter that we, you get tired. You need, for each universality class, you need to do a lot of calculation. I mean, a lot of calculation numerically. Yeah, it's completely clear that there is no reason why we shouldn't do the 38. It's just a matter of we're only 3 people, and at some point we need to stop. So we decide half was okay. Sorry? The Hilbert, what would the Hilbert space of? But I'm not sure if I understand. So about jetty gravity? You mean the final part, the final? Okay, sorry. Yeah. Okay, no, basically what we said is that it's possible to map, you can map, sorry. So it's possible to map JT. I didn't do that. It was done before. So you can map JT gravity to a model that is a model of one particle in an imaginary magnetic field on some hyperbolic plane. So it's just a mathematical thing that you can do. That was done by the student of Maldacena. And then this was done by this student of Maldacena. Then what we did is that then basically you transform the problem of gravity to a problem of one body, quantum mechanics. Now, what he did was still for a rigid geometry, but then you can study fluctuation of this geometry. And then study what is the dynamic of this fluctuation of this geometry for one particle, because actually these people in the quantum chaos have studied that before. So we put together these two things. Second.
No.
No. Yes.
Okay.